Hey everybody, welcome back to chemistry. And today what I want to talk about is writing something called a Lewis structure. And so what a Lewis structure is a simple drawing or representation of a molecule. And in that drawing you'll see lines and dots. Lines will be between the atoms in the molecule and represent a shared pair of electrons, while dots will be sort of on the outsides of the atoms, and they represent lone pairs. So Lewis structures are pretty important to learn because if you go on to organic chemistry, you're going to have to draw a lot of Lewis structures. And so it's pretty important now, I would say, to learn how to do this correctly. So there are certain things I can tell you to do that I hope will be able to help you in that goal. So I have some steps here on how to write a Lewis structure, and so let me just kind of quickly go over them, only because I'm going to be doing a bunch of examples on the glass board. So one of the first things you'll have to do is you're going to be given a formula, say like N2 or CHCl3, something like that. And from the formula, what you'll have to first do is draw a skeletal structure of the molecule, meaning you're going to have to use elemental symbols and place them in space in reasonable positions. After you've done that, the second step is to count the total number of valence electrons that are contributed by all atoms in this structure. The next step is, once you figure out the total number of valence electrons, you think about them in terms of pairs. The first pairs you deal with, you stick in between atoms, and usually it's between some kind of central atom and a peripheral atom. After that, you'll have some valence electrons that are left, and there you put those as dots, as lone pairs around first the peripheral atoms, and once they have a octet or something near an octet of electrons, then you can put electrons around the central atom. Then the goal after you've done that is to make sure that all atoms except hydrogen have an octet, meaning they have 8 electrons that surround them. With hydrogen, it's not 8 electrons or an octet, it's only 2 electrons, which is called a duet. And so to finally finish the structure, if you're in a situation where you've drawn the structure but you don't really have octets around the atoms, it may be necessary to move electrons from the lone pairs into the bonds to make sure that all atoms have an octet. Okay, so what I'm going to do is, for several molecules, is I'm going to draw out a Lewis structure. And I'll show you how to do that in detail. And then what I'm going to do is I'm going to look at the electronegativity difference between the atoms in the bond, because that determines the bond polarity. And that is important to be able to figure out. And then finally, what I want to do is, once we figure out the bond polarity, I want to figure out if there is sidedness to the molecule. In other words, is there a side which has a relative excess of charge, and so you would represent that with a delta negative sign? And is there another side of the molecule with a relative deficiency of charge, which you would represent as a delta positive? So let's go ahead and begin. So the first one I want to do is maybe one of the simplest Lewis structures to draw, which is that for water. So you'll be given a formula for water, for example, and you know what that is, it's H2O. So the first thing you need to do is you need to write out a skeletal structure indicating where you think the nuclei of these 3 atoms are going to be in space. So let me show you a couple of possibilities here. So we have 2 hydrogens and an oxygen. So maybe one hydrogen nuclei might be here, another one might be here, and another one might be there. That may be a possibility. Or maybe another possibility is have hydrogen here and then oxygen in the middle and then hydrogen on the end. So is there an answer that is correct between these 2 skeletal structures? And the answer is yes. This one's correct and this one's not right. And so one of the rules you'll have to remember about drawing Lewis structures is that hydrogens are always at the ends of the molecule. They are at the sort of the termini of the molecule. So here with this skeletal structure, we don't have a hydrogen in the end. It's in the middle, and you can't have that. So you cannot use this representation here. this one is a good one to start with. Okay, so now what I want to do is count the total number of valence electrons for all atoms involved in the structure. So we have 1 oxygen and 2 hydrogens. So oxygen has 6 valence electrons, and then hydrogen, as you probably know, has 1 valence electron, but there are 2 of them. So from the hydrogen atoms, you have a total of 2 valence electrons in the structure. So all total, we have 6 valence electrons from oxygen, 2 electrons from the 2 hydrogens, so we have 8 valence electrons. And so we want to think about this in terms of pairs. So we have 8 valence electrons. You can think of it as 4 pairs of valence electrons. So I'm going to write 4 pairs here. Okay, so what is the next step? The next step is we're going to distribute 4 pairs of electrons around this skeletal structure in a way that sort of makes chemical sense. And so there are steps to that. So the first step is to first connect oxygens with hydrogens. You want to bond these atoms together. And so you might know at this point that within a bond, whether it's an ionic bond or a covalent bond, here we're going to be dealing with molecules mostly that are covalent bonds, you have a pair of electrons usually that form a bond. Now you can have more than that, but to start with, we're just going to connect atoms with a pair of electrons. So we have 4 pairs here, so I'm going to connect oxygen and hydrogen with this pair of electrons here, and then oxygen and hydrogen with this pair of electrons here. So now we're down to 2 pairs. We have 2 more pairs to put on the structure. So one question you can ask is, are you allowed to put another pair, say, around this hydrogen here? And the answer is no. And the reason is we're going to count how many electrons these atoms have in a minute. But when we do the count, what you'll see is that hydrogen really only has 2 electrons associated with it, and that's all it can have. It cannot have more than that. It cannot have 8 or an octet. It cannot have any more than that. So if hydrogen cannot accept any more electrons, then the other 2 pairs will go around oxygen. Oxygen can accept 2 pairs here. And so here it can accept up to 8 electrons. And so it looks like oxygen has a total of 8 electrons. Okay, so the next thing we're going to do is to confirm that we've written a good Lewis structure. We have to make sure that the hydrogens here only have a duet, a pair of electrons, while other atoms have an octet or 8 electrons. So let's do some electron counting. So let's first count the electrons associated with hydrogen. So you see we have a pair shared here between this left hydrogen and this oxygen. So this pair here that is shared, that is considered also in the hydrogen count. So hydrogen has 2 electrons, and so that's good. That's what we want. And so this hydrogen on the right also has 2 electrons because this pair is shared between the oxygen and the hydrogen, and it's considered in the hydrogen count. So this hydrogen here as well has 2 electrons. Now let's count the electrons associated with oxygen. So this pair up here is with oxygen. This pair is up here. How about the pair between oxygen and hydrogen? Those are also considered in oxygen's electron count. Again, they're shared between the oxygen and the hydrogen here. So when you count the electrons for oxygen, you want the lone pairs out here, but also you want to count the ones that are shared with the hydrogens. So what we can see is that these hydrogens have a duet, which makes the hydrogen atom stable. And then this oxygen has an octet, which makes the atom stable. So we have used up all 8 electrons. So this is, it looks like the atoms in this structure will be stable. So to make a final Lewis structure, the last thing you do is you want to draw lines for shared pairs. And so we have a shared pair between this oxygen and this hydrogen here. So we draw a line for that. You do not draw lines for lone pairs. Lone pairs on this oxygen atom here are just kept as dots. So the final Lewis structure is this. So I've drawn lines there for the shared pairs, and we have dots for the lone pairs. Now, a question that's often asked is, do you have to put the hydrogen on the opposite side of the other hydrogen from the oxygen. And that's not necessary to do. So an equivalent Lewis structure, which is equally good, is if you happen to put the hydrogen at an angle here like 90 degrees. And so that will work just fine too. So either of these structures is a good Lewis structure for water. Now, the next thing I want to talk a little bit about is evaluating the polarity of the bond between oxygen and hydrogen. So let me sort of remind you how you do that. So you have to hopefully have a table of electronegativities and look up the electronegativities of the atoms. So I kind of know that oxygen has an electronegativity of 3.5 and hydrogen has an electronegativity of 2.1. So you can see that they have different electronegativities. And so if you wanted to, you can calculate the difference of electronegativity between these atoms. So the difference of electronegativity is just you take the higher electronegativity and subtract the lower electronegativity. And then the difference of electronegativity is 1.4. So you look at that number, and from that number, you can sort of evaluate the kind of bond here that occurs between oxygen and hydrogen. You might remember from an earlier presentation, if the difference of electronegativity is between 0 and 0.4, that is considered a relatively non-polar covalent bond. If it's between 0.4, say 0.5 and 2, this bond here is considered a polar covalent bond. And if you are above 2, then you're really into the ionic bond range. So right here you can see that this kind of characterizes this bond as polar covalent. So here, this bond here is polar covalent. Now we have an identical bond to a second hydrogen atom here, so this bond as well is polar covalent. So let's talk about what that means in terms of the charge distribution, the electron distribution of the shared pair between the different atoms. So let me draw this again. So we have water here. I'm just going to draw it like this time. So oxygen has the greater electronegativity. So what that means is that when you consider a shared pair of electrons here between oxygen and hydrogen, remind yourself that these shared pair is kind of wandering around both oxygen and hydrogen. Slight digression, you might remember that oxygen also has these lone pairs. These lone pairs are localized in these positions around oxygen, so they tend not to be shared with the hydrogens. But looking at the shared pair here between this oxygen and hydrogen, it will wander around between the oxygen nuclei and the hydrogen nuclei. But the electronegativity of oxygen is much greater than the electronegativity for hydrogen. And remember what electronegativity is? It's a ranking of an atom's nuclei attraction for a shared pair of electrons. So if oxygen has electronegativity 3.5 and hydrogen has electronegativity of 2.1, in that tug of war for the shared pair, oxygen will definitely win. So the electrons here will spend a lot more time around oxygen and not as much time around hydrogen. Same thing here in this bond. The shared pair here will spend a lot of time around oxygen, not as much time around hydrogen. And so because the electrons in the shared pair are spending a disproportionate amount of time around the oxygen, there are electrons, so we indicate that we get sort of more electron density around the oxygen by putting a delta negative here near the oxygen, and the hydrogen here will be a delta positive. Okay, so that is the Lewis structure of water, and that sort of explains the electron distribution of the shared pairs in the structure. So let's move on to another one, a little bit more difficult. Okay, so the next molecule we're going to do is gaseous diatomic oxygen. So this is a little more difficult, but not too bad. Let me get a good pen here. I guess this will work. All right. So we have oxygen here. So can you draw a Lewis structure for oxygen? Again, a little trickier. So the first step is to draw out the skeletal structure, which shows where the nuclei of these atoms are in space. So I'll have one oxygen there and one oxygen there. So that was easy enough. Okay, the next step is to figure out how many total valence electrons are we dealing with in this molecule. So we have oxygen, and each oxygen atom has 6 valence electrons, and there are 2 of them. And so you have a total of 12 valence electrons. And so you have a total of 12 valence electrons, you have 6 pairs you have to deal with. Okay, so far so good. So do you remember how we deal with the pairs of electrons? The first thing we do is we bond atoms together with a pair. So here I'm putting a pair here, so now we're down to 5 pairs that we have to deal with. Okay, so where do they go? Okay, so you can distribute them around the 2 oxygen atoms. So here's pair 2, here's pair 3, here's pair 4, here's pair 5, and then I'll just arbitrarily put pair 6 here on this oxygen atom. So that is fine. We've done everything perfectly fine at this point. So now what we do is we check to make sure that our atoms there have 8 electrons. They have octets. So let's look at the left oxygen. And so you can see it has 3 pairs here and this shared pair. So this oxygen has 4 pairs of electrons, so it has an octet. But how about this oxygen here? So it has these 2 pairs here, but also you count the shared pair here. And so here, the oxygen atom on the right here does not have an octet. It only has 6 electrons. And so we have a problem here. So let me redraw the structure and then talk about how we solve the problem here. So the problem is this. One of the oxygen atoms has an octet and the other one doesn't. So how do we sort of fix this so that both atoms have octets? Well, what you can do is if you're in this situation, you can move lone pairs in between or into between atoms, and then that can help solve the problem. So let's just try that. So let's just take this lone pair here on this left oxygen here on the bottom here and move it between the oxygen atoms like that. And let's just rewrite the structure. So I'm just going to rewrite it down here. So this is what I have. Okay, and I move this pair here, and there was already another pair there, right? So that's still there. And so here are the other pairs. Okay, so we've moved that lone pair into the bond between the 2 oxygen atoms. Now let's do an octet count. So the oxygen on the left, it has this pair, and then these 2 shared pairs count in this oxygen's electron count. So it looks like we have 8 electrons here for this oxygen. It has an octet. The oxygen on the right, a pair here, and then also these 2 shared pairs are counted as well. And so we have an octet here for the oxygen on the right. So it looks like both atoms have octets. So this is a stable structure. And so from here we can finish off the Lewis structure by drawing lines for a shared pair of electrons. So let's do that now. So we have an oxygen atom here, an oxygen atom here, and you can see that we have 2 shared pairs. So we draw 2 lines like this, and then you have these lone pairs here that are still there in the structure. So this is a correct Lewis structure for O2. So maybe you heard in some past class that oxygen has a double bond, and now you can sort of see why it does have a double bond is because you needed a double bond so that both oxygen atoms could have octets. And so the way it got it was it basically moved one of its lone pairs into the bond between the oxygen atoms. And so when it has a double bond, it gets an octet for both atoms and it's very stable. Okay, finally, let's look and figure out if this double bond, this bond between the 2 oxygen atoms, is it a non-polar covalent, is it a polar covalent, or is it an ionic bond? So the way you evaluate that is looking at the difference electronegativities of these oxygen atoms. So this oxygen atom here has electronegativity of 3.5, and this oxygen atom here has the same electronegativity of 3.5. Let me get a better pen. That pen's pooping out. So this is 3.5 and this is 3.5. So the difference of electronegativity is going to be 3.5 minus 3.5, which is equal to 0. Okay, so what that means is, let me draw oxygen again here. So we have oxygen here with a double bond. And so the difference in electronegativity between the 2 atoms, as expected, is 0. So what that predicts is because these 2 oxygen atoms have equal electronegativity, these 4 electrons in the bond, the 2 shared pairs, are going to spend equal amounts of time around each of these oxygen atoms. And so if that is the case, this is a non-polar covalent bond that occurs between the oxygen atoms. Also, another question you can ask is this molecule lopsided in terms of charge? In other words, does it have a delta negative end where it has a relatively excess of electrons and a delta positive end? And the answer is no, because the shared pair is spending equal amounts of time around these oxygen atoms. So there's no delta positive or delta negative to this. So that's basically a non-polar covalent bond between the two oxygen atoms. Okay, so let's move on to the next one. Okay. Okay, so how about NH3? So NH3 is ammonia. NH3 is ammonia. So can you draw a Lewis structure for that? So I'm going to go ahead and draw a skeletal structure. And so what I've done is I put the hydrogens on the outside or the termini of the molecule, and the nitrogen is in the center. So that's probably the best thing to do. Okay, so nitrogen has 5 valence electrons. Hydrogen has 3 valence electrons. Excuse me, hydrogen has 1 valence electron. So it has 1 valence electron, but there are 3 of them for a total of 3 valence electrons contributed by the 3 hydrogen atoms. So the total number of valence electrons in NH3 is 8, and so that is 4 pairs. And so can you distribute the 4 pairs fairly in this molecule? So you first have to bond this nitrogen and this hydrogen. So that's 1 pair. This pair goes here to bond these 2 atoms. This pair, third pair, goes to that to bond this nitrogen and this hydrogen. And then we have 1 more pair. So where does it go? So you might remember that hydrogen can only accept a duet of electrons, and it has that in all examples because it has a shared pair. So where does that extra pair go? It goes to nitrogen right there. Okay, so let me redraw this a little bit more carefully. So we'll put that pair there, here, here, and here, so that's just a little bit clearer. Let me get rid of that. Okay, so that is looks like a reasonable Lewis structure for NH3, which is ammonia. But let's check to make sure that hydrogens have duets, and this nitrogen in the center has 8 electron octets. So this hydrogen has a duet, this hydrogen has a duet, this hydrogen has a duet. So does the nitrogen in the center have an octet? Yes. And so again, you can count the shared pairs in nitrogen's count along with its lone pair. So nitrogen has 8 electrons. So the Lewis structure should be this. It should be H, N. Don't forget about the lone pair around the nitrogen there. And then we have hydrogen here. Now, if you wanted to, you could evaluate whether these bonds from nitrogen to hydrogen, are they non-polar covalent, polar covalent, or ionic. So I encourage you to do so on your own. I'll let you do that for a few moments now and maybe ask you a question. Okay, so you have maybe figured out here that nitrogen has an electronegativity. If you looked it up, it has an electronegativity of 3.0. Hydrogen has an electronegativity of 2.1. So the difference of electronegativity between the nitrogen and the hydrogen is 3.0 minus 2.1, which is 0.9. So that would classify a bond between nitrogen and hydrogen with an electronegativity difference of 0.9 as being a polar covalent bond. So these are polar covalent bonds. And so as you might expect, nitrogen has the greater electronegativity, so it's going to be delta negative. Well, each of these hydrogens, because they have lesser electronegativities, will be delta positives. Okay, so let's move on. Okay, carbon tetrachloride, so CCl4. So how do we place the atoms in space? So let me show you a couple of possibilities. So maybe one possibility is having a chlorine in the center and maybe a carbon on the outside. And then maybe you can have chlorine surrounding the internal chlorine like this, or another possibility is having carbon in the center and then chlorines on the outside. So which possibility is it? Well, another rule you should know, in addition to the fact that hydrogens can only be on the outside, the periphery or the termini of the molecule, another rule you should know is that if you have a choice between carbon and chlorine or other atoms, and you're trying to choose which one should be in the center, the one that should be in the center should be the atom with the lesser electronegativity. So hopefully you'll have maybe a chart of electronegativity, and you can look up carbon's electronegativity and see it's 2.5. Chlorine's electronegativity is 3.0. So carbon has the slightly lesser electronegativity, so it should be in the center. So this skeletal structure is not correct, so let me redraw the correct one. So there's carbon in the center, and then chlorines on the outside. There are 4 of them. Okay, let's do a count of valence electrons. So carbon has 4 valence electrons. Chlorine has 7 valence electrons, but you have 4 of them for a total of 28 electrons. So you have 32 electrons you're dealing with total. So that is 16 pairs. Okay, so that's a lot of electrons. Okay, so 16 pairs. Now the first pair goes here, second one goes here, third here, fourth here, because we have to connect the atoms first by pairs. So we're down to 12, right? We have 12 left. So there are 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So this is a reasonably good structure. And so let me explain why it is a good structure, and you may already know, is because each of these chlorines here has 8 electrons, so it has an octet. And then the carbon in the middle, again, you can count the shared electrons with chlorine as part of its count. So the carbon in the middle has 8 electrons as well, so it also has an octet. So this isn't considered a perfect Lewis structure. What you have to do to write a perfect Lewis structure is to draw lines for the shared pair of electrons. So you have carbon here, and then we have a chlorine here, a chlorine here, a chlorine here, a chlorine here, and then don't forget in your final Lewis structure to put lone pairs around the chlorine atoms like this. Okay, so this should be a good Lewis structure. Okay, so you can maybe figure out on your own whether the bonds between carbon and chlorine are either non-polar covalent, polar covalent, or ionic. So I'll let you figure that out on your own. Okay, so let's move on to the next molecule.